Hey guys, this lesson is going to be for trigonometry basics. It's a total introduction to trigonometry, to the basic trigonometric functions and what they're used for and why we need them and a bit of why they work. We'll have a follow-up lesson that sort of talks about the history of trigonometry, where it all comes from, the words that we use, the beginnings, if you will. So, first things first. I have drawn for us a right triangle. Trigonometry, in the beginning, focuses on right triangles. We do use trigonometry for angles outside of right triangles, but we begin with the ratios in this regard. I've drawn for us a triangle, and this is actually drawn to scale. I used a ruler and sketched out a triangle that has this side over here, it's 4 centimeters, and the hypotenuse, which is across from our 90-degree angle, that is 10 centimeters. And within it, I also drew a smaller triangle. They share this same angle here. The angle I labeled in blue is theta. That is the Greek letter theta. Theta is spelled T-H-E-T-A. So you might see people draw it here with the squiggle across the middle, and other times people will draw it with a straight line across. Those are both theta. They're both acceptable. It's sort of like a capital and a lowercase version of the same letter. So you'll see in math, we often use Greek letters to represent unknown angles. In geometry, you may more commonly refer to angles with capital letters and sides with lowercase letters. When we have a right triangle, the other two angles in a triangle have to be acute. A triangle has a total of 180 degrees. A right angle is 90. That means that the other two angles have to share 90 degrees between them. And since an acute angle has between 0 and 90 degrees, that means the other two angles will both be acute angles. We're going to focus on this angle theta for right now, but you could always change your perspective when you're dealing with trigonometry. When we're dealing with trigonometry, right triangle trigonometry, we focus on the acute angles and not the right angle. That's not to say that you can't use trigonometry with right angles, but right triangle trigonometry deals with acute angles in right triangles. Okay? So our perspective, meaning where we're looking at the rest of the triangle from, is going to be from this acute angle theta, from this bottom left corner. Here's a different acute angle. That's not theta. We didn't label it theta. We're not going to look from this perspective. We're going to look from this one right over here. Now, we're given an acute angle theta right over here. I don't know how big it is. I haven't measured it. I don't have a protractor handy, and that's okay because we live in a world where if I have a ruler and I know some measurements, I can use a calculator. Here, we'll call this side the opposite side. So we need to name everything. Opposite will mean it's across from it, okay? It means that the side is not adjacent to the angle. Adjacent means next to. Here we have theta. The sides that are both adjacent to it technically are going to be this one right over here, going completely horizontal, and this one right here. Now, this adjacent side happens to have a very special name, or if we're looking at the big triangle, this one. The adjacent side that I'm tracing over right now is known as the hypotenuse. This adjacent side is not the longest side of the triangle. This adjacent side will just be referred to as adjacent. This side is hypotenuse, this side is adjacent, and this side, while I could call it across, but those both start with A, and that's sort of going to mess us up later, we will call this side the opposite side. So I'm going to take a second to draw out and label a triangle now for you to also copy into your notes, and it will be important for reference. And actually what I'll do is I'll draw this triangle from 2, maybe 3 perspectives just so you can see how where you're looking at the triangle from will affect which side is considered the opposite side and which side is considered the adjacent side or the hypotenuse, okay? What I've done is I drew a few different triangles just so you can see that the side that is considered opposite, I always put that one in orange. The opposite side might not be in the same place on every picture, but it will always be across or opposite from the angle theta that we're looking at the rest of the triangle from. So it's like you're standing here. The side adjacent to it is next to it and touching and creating that angle. But so is the hypotenuse. However, the hypotenuse is more specific because it's also across from the largest angle, and in a right triangle, that's always the 90-degree angle. So we have the hypotenuse in pink in all of these pictures. We have the opposite in orange in all of these pictures, and the adjacent is always drawn and highlighted in green. Now that we know how to label the sides of a triangle, and this should not be underestimated, this is really important to know. The next thing we have to address is that if you have at least two sides, if not all three, of a right triangle, and keep in mind, Pythagorean theorem says that if you have two sides of a right triangle, that you could find that third side. So having two sides of a right triangle is the same as having all three sides of a right triangle. If we have two sides of a right triangle, and we know it's a right triangle, we can actually figure out how big this angle is. We can find the measure of theta. Now I drew theta and marked it inside the angle in a different place in all these triangles. Theta is how big the angle is. It doesn't matter if I draw this little arrow right here far out, or if I drew it even further out, or a little bit closer to the inside. The measure of an angle is the same, no matter what. When you use a protractor, you could really see that it doesn't matter how long, it's not a length, it's how big we open up, how much we swept out. We're going to want to figure out the measure of theta. I drew for us two triangles, one within the other. From earlier sections, we should know a little bit about this triangle that I drew in black and this triangle I drew in red. We see here that these triangles, while they're both right triangles, they also share this angle right over here. We also have the hypotenuse of each of them and the leg of each of them, the same leg. While they're not congruent, 2 and 5 are not congruent to 4 and 10. What is it that we know about the red and the black triangle? 5 is the hypotenuse, 10 is the hypotenuse. 2 is the opposite leg, 4 is the opposite leg. If you said that you know that these two triangles are similar to one another, then you would be correct. They also have a scale factor. The scale factor, depending on how we phrase it, we can say, what is the scale factor from the red to the black? What do you have to scale the red triangle by to get the black triangle? That scale factor would be 2. If we were going from the black triangle to the red triangle, that scale factor would be 1/2. Now that we know we have two similar triangles, we're going to do a little bit of a discovery so we actually understand where the trig function's logic comes from and why it works. Theta over here, our unknown angle. We know that this angle measure is the same for both the red triangle and the black triangle. I also have the opposite and hypotenuse, the opposite and hypotenuse for each of these triangles. If I look at the ratio of 2/5, the opposite leg over the hypotenuse, 2/5 reduces to just 2/5. As a decimal, it's 0.4. On the larger triangle, the ratio of the opposite to the hypotenuse, even though it's not congruent to the red triangle. The black triangle is merely similar. The ratio of the opposite over the hypotenuse, which was 4/10, even if we included the units, 4 centimeters over 10 centimeters. Centimeters is going to reduce from both the numerator and denominator. We're only left with 4/10, which further reduces to 2/5. Let's take a second and write that down. So what we have now is the ratio of the opposite leg to the hypotenuse for each of these two triangles happens to reduce down to 2/5. Another thing to keep in mind is the ratio between any two legs of the right triangle won't have any units on it because the units should match on the numerator and denominator, and then that will reduce down or simplify to 1. So we will not have units when working with ratios. The fact that these triangles, although similar and not congruent, both have the same ratio tells us that the angle that we are finding these sides from that perspective, okay? The angle where we started, its measurement should be the same for both triangles because they both have the same ratio of opposite to hypotenuse. So whether these were in centimeters or in miles, feet or yards, the ratio of 2:5 for the opposite over the hypotenuse. The fact that it's 2/5 for both triangles tells us that the theta value or the angle measure is the same in both triangles. And that completely makes sense here because of how we happen to construct this picture. The trigonometric function we use when describing ratios of opposite over hypotenuse has a name. The name of that trig function is the sine function. In math, the sine is a trigonometric function of an angle. The sine of an acute angle is defined in the context of a right triangle for a specific angle. The sine of an acute angle theta is equal to the ratio opposite side over hypotenuse. Algebraically, we write that out as sine theta equals opposite over hypotenuse. SIN, which looks like the word sin, is the abbreviation of sine. I know we're only cutting off one letter. It's not a major abbreviation, but there are 5 other trig functions, so we abbreviate all of them down to just 3 letters, so it's not that strange once we learn every trig function. Just as another side comment, since there are 3 sides on a triangle, a combination of 2 sides, opposite over hypotenuse in this case, gives us 1 trig function. There are 6 ways to combine any 2 of the 3 sides. That's why we have 6 different trigonometric functions. Opposite over hypotenuse is the ratio attributed to sine. There is also going to be a trig function for the adjacent over hypotenuse, for the opposite over adjacent, and then for each of those reciprocals, hypotenuse over opposite, hypotenuse over adjacent, and then adjacent over opposite. That's why there are 6 trigonometric functions. All right, we're going to start off with setting up some notes for the 3 basic trig functions. I just have this rock stone crystal up here on the corner page because it keeps curling up and it messes up the lighting, so pay no mind. The 3 basic trig functions. The first one we just saw was sine. We're going to write out the full spelling of their names first. After sine, we're going to see cosine, and this co in front is the same co we saw at the beginning of the word complementary. So there is a reason behind the fact that we have the word sine and then we have the cosine. So this is going to be related to sine in the sense that they are what we call a cofunction, and in the sense that there is a relationship with their complementary angles, but one thing at a time. The third of the basic trig functions is tangent. Next thing I'm going to write down is the abbreviation and theta. I'm also going to write down what it's equal to, and I'm going to abbreviate only using some shorthand. So what we have here for the three basic trig functions is sine of theta will be equal to the opposite over hypotenuse. The cosine of theta equals adjacent over hypotenuse. And the tangent of theta is equal to the opposite over adjacent. So as long as you have two sides of a triangle, you can use one of these three trig functions to figure out the angle. Now I'm going to write a little bit of a note underneath each of these trig functions. What I put underneath cosine was just a drawing of a triangle, and I labeled if theta is in the bottom left corner, like so, the adjacent and the hypotenuse sides are the ones that are labeled. We don't have the opposite, which would be over there. And then for tangent, I changed the perspective. I looked at theta as being in the top right corner. The adjacent side will still be the side next to the angle, except now it's over here in the picture. It's not going to be down here. It's all about the perspective, and this is now the opposite side. Another thing that you have to do with your ratios for your trig functions is you always need to rationalize your denominators. And you should always reduce your fraction completely. Questions might just ask you, what is the sine of theta in the picture below? What is the cosine of theta in the picture below? In that case, you're just going to write out a fraction. You don't need to change it to a decimal. Before we move on to some examples, I want to give you a quick mnemonic device that is more or less taught in every trigonometry unit in any math class. And that mnemonic device is called SOHCAHTOA. It has a sort of rhythm to it, so people tend to have no problem memorizing it. Oh, too bad I'm already writing the wrong thing. I'll make that look cute in a second. But this mnemonic device would be absolutely useless if you don't know how to spell it. In addition to being able to spell this mnemonic device, we also need to know what it means. So, get it? So, So what this means is the sine ratio is opposite over hypotenuse, cosine ratio is adjacent over hypotenuse, and tangent ratio is opposite over adjacent. So it sort of just helps you memorize them.